Welcome to General Chemistry Mini Lecture Series, Lecture 44, Bond Energy, Strength, and Length. Chemical bonds in reactants during chemical reactions are broken, and new chemical bonds are formed to create products. The delta H of reaction can be calculated using bond energy of bonds broken and bonds formed, or bonds created. Bond energy is defined as the amount of energy it takes to break 1 mole of a bond in a compound in the gaseous state. The more electrons two atoms share, the stronger the covalent bond. For example, in triple bond, there are 6 electrons, and in this case, carbon-carbon triple bond, 6 electrons are shared by 2 carbon atoms. The bond energy is 837 kilojoules, versus carbon-carbon single bond, only 2 electrons are shared by the 2 carbon atoms, and the bond energy is much, much smaller, 347 kilojoules. The same thing is true for carbon-nitrogen triple bond, double bond, and single bond. The shorter the covalent bond, the stronger the bond. This BRF bond is the shortest among these 3 bonds, and then it has the highest energy, 237 kilojoules. Bromine-chlorine bond is longer than bromine-fluorine bond. That's why the energy is lower than the energy here. And bromine-bromine bond is the longest, and therefore this BR-BR bond has the lowest bond energy. Bonds become weaker down a column because of the increasing of atomic size. When it comes to the actual bond energy, it depends on the surrounding atoms and other factors. So therefore, we use average bond energies in estimating the delta H of reaction. The bond breaking process is endothermic. That's why delta H has a positive sign. It simply means it takes energy, or energy needs to be added to the system in order to break those chemical bonds. The opposite is true for bond making process. Bond formation process is exothermic with a negative sign for delta H. In other words, energy or heat is released when bonds are formed. The delta H of reaction can be calculated using the sum of delta H for bonds broken plus the sum of delta H for bonds formed. And the bonds broken are actually the bonds for the reactants. Bonds formed are the bonds for products. So therefore, those 2 equations are actually the same. However, if we consider all bonds energy are positive, it is easier to using the following equation to calculate the delta H of reaction. So using this equation, we don't need to worry about positive sign should be used for bonds broken, negative sign has to be used for bonds formed. All of the delta H for bonds broken or bonds formed, we just use positive values. But instead of adding them, we subtract the delta H values for bonds formed from the delta H values for bonds broken, or the sum of delta H for bonds in reactants subtracted by the sum of delta H value for bonds in product. Personally, I like to use this equation so that I don't need to worry about the positive sign for bonds broken and the negative sign for bonds formed. Now let's work on the first example in lecture 44. we need to estimate the enthalpy of this reaction. Hydrogen reacting with oxygen forming peroxide. This reaction involves breaking 1 mole of H single bond and 1 mole of OO double bond, and making 2 moles of HO bond and 1 mole of OO bond. You may get lost. Why 2 moles of HO bond? Let's write this reaction in another way. H2, that's H and H. It's 1 single bond. O2 reacting with O2, OO double bond. Then H2O2. So we write that in this way, HOOH. That's why you can see there are 2 moles, you see, in each mole of H2O2. There are 2 moles of HO single bond. That's why we have this 2 moles of HO single bond here, and 1 mole of OO single bond. Okay, so those are bonds broken, those are bonds formed, and you can find the average bond energies from table 44-1. We'll use this key equation, considering all of those bond energy values as positive ones. The sum of bonds broken or reactants, 1 mole of HH single bond and 1 mole of OO double bond, then subtracted by 2 moles of HO single bond and 1 mole of OO single bond. The next step, we just plug in those values. So this calculation results in negative 136 kilojoules as the enthalpy for this reaction. Let's work on bond length now. Bond length is the distance between the nuclei of bonded atoms. In other words, bond length equals the sum of the covalent radius of the 2 bonded atoms. For example, in chlorine diatomic molecule, the bond length is 198 picometers, and the chlorine covalent radius is half of that, 99 picometers. In ionic compound, for example, hydrogen fluoride, the bond length is 92 picometers. That's hydrogen ion radius plus fluoride ion radius. Because the actual bond length depends on the other atoms around the bond, so we often use the bond length average for similar bonds from many compounds. For example, the CO double bond length in carbon dioxide is shorter than the CO double bond in formaldehyde. Therefore, we use the average CO double bond length of 123 picometers. The more electron 2 atoms share, the shorter the covalent bond. Again, we use the carbon-carbon single, double, triple bonds to show this effect. In carbon-carbon triple bond, 6 electrons are shared, and the bond length is the shortest, 120 picometers, versus 134 for carbon-carbon double bond and 154 picometers for carbon-carbon single bond. The same trend is true for CN triple, double, and single bond. Bond length decrease from left to right across a period. If one of the atoms is the same, you see in this example here, carbon exists in all three single bonds, and now the bond length decreases from left to right across the period depending on the other atom bonded with carbon atom. So that's why carbon-carbon single bond is longer than carbon-nitrogen single bond, and then carbon-oxygen is the shortest among this group. The bond length increases down a column. If you look at fluorine-fluorine bond, it's 144 picometers. Chlorine-chlorine single bond is longer than fluorine-fluorine single bond. And further down the halogens column, or group 7A column, bromine-bromine single bond is the longest. In general, as bonds becomes longer, they also get weaker. So therefore, the bond length is decreased. This table shows the average bond length in picometers, and those are the single bonds, and here are the multiple bonds. This table demonstrates the relationships between bond order, bond length, and bond energy. As bond order increases, bond length decreases, bond energy increases. That's the relationship between bond order, average bond length, and average bond energy. Now let's rank the following bonds in order of increasing bond length and bond strength. Really two questions. One is the trend for bond length, the second one for bond strength. Now, bond length. Because the bond order is one for all three bonds, and one of the atoms in each bond is sulfur, then the bond length is directly proportional to the radius of each bonded halogen. The size of the bond radius follows this trend. So because the halogens are in the same group and atomic size increases from top to bottom, therefore the order of decreasing bond length should be sulfur fluorine with the shortest single bond, followed by sulfur chlorine. This SCl bond is longer than SF bond, and then sulfur bromide bond is the longest among those three bonds. That's for bond length. Now let's work on the bond strength. Because the bond length is inversely related to the bond strength, so therefore the order of increasing bond strength should be the opposite of the trend shown here. Now the SBr bond is the weakest, and SF bond is the strongest, because SF bond is the shortest and SBr bond is the longest. Let's work on example 3 in lecture 44. We need to rank those bonds in order of decreasing bond length and bond strength. Let's work on bond length first. Because the same two atoms are bonded in all three bonds, but the bond order changes: single bond, double bond, and triple bond. The bond length decreases and the bond order increases. Therefore, for the bond length, CO single bond is the longest and CO triple bond is the shortest. Again, the bond length is inversely related to bond strength. Therefore, the order of decreasing bond strength is CO triple bond has the strongest strength and CO single bond has the weakest bond strength. That's it for lecture 44. If this is helpful, please subscribe. You are also welcome to recommend this channel to other students who are also studying chemistry. I will see you guys in lecture 45, molecular geometry.